Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In the previous video, we covered the order condition, which stated that you need at least as many instruments as endogenous variables. But counting instruments is not enough, and that's why we need what we call the rank condition, which answers the question, do your instruments provide independent information? The intuition behind it is quite simple. So imagine that you have two instruments, Z1 and Z2. The order condition is satisfied, okay, because let's say that you had one endogenous variable, X, but now suppose that Z1 and Z2 are perfectly correlated. So let's say the correlation between Z1 and Z2 as variables is exactly 1. Okay? So they move together in exactly the same way. So they are telling exactly the same story about X. In this case, having two instruments gives you no more information than actually having one instrument. And the rank condition captures exactly this idea formally, okay? The name actually comes from linear algebra because the rank of a matrix measures how many linearly independent rows or columns it has. If you remember in the previous video, we talked about this idea that you have to think as if you're solving a system of equations when we talked about over-identified, just identified, or under-identified. So if we were to imagine this comes from linear algebra, then you're thinking of a matrix, okay? And the rank condition failure means that your instrument matrix doesn't have enough independent variation, okay? So what does then the rank condition require of you? The rank condition requires that the instruments provide sufficiently independent variation in the endogenous variables. More precisely, so enough independent information, or in other words, it requires that the matrix of the first stage coefficients must have full rank. I'm going to put this in a box because this is a very important result that you need to remember, okay? What I'm saying in plain English is each instrument must be contributing something genuinely different to the prediction of the endogenous variable, okay? In the simple case where you've got one endogenous variable, one instrument, the rank condition is literally saying that pi1 needs to be different from 0. So the simple case, one endogenous, one Z, okay? That's what the rank condition simplifies to. And in a sense, that's literally just the relevance condition. So the rank condition only becomes distinct from relevance when you actually have multiple endogenous variables. What happens when the rank condition fails? The rank condition fails when instruments are too collinear, meaning they provide essentially the same information. So imagine that in this particular case when we said that correlation Z1 and Z2 is 1, imagine that Z1 is distance to nearest university, while Z2 is distance to nearest college, okay? If universities and colleges are always located in the same places, then these two instruments move together perfectly. They are not really two independent sources of variation. They are one source measured twice. So the rank condition would definitely fail in here. And even though technically you'd have the order condition being satisfied. So this is why instrument quality matters just as much as instrument quantity, okay? So instrument quality matters, okay? Two highly collinear instruments are barely better than one. What happens to the rank condition then when you have multiple endogenous variables? The rank condition becomes most important and most subtle when you have multiple endogenous variables. If, let's say, we assume that you have X1 as education and X2 as your work experience, both are endogenous variables. And let's assume that you have two instrumental variables, Z1 and Z2. The rank condition requires you that the Z1 and Z2 affect X1 and X2 sufficiently in different ways. But if Z1 affects only X1 and Z2 affects X2, that's perfect. It means each instrument is doing a different job, and you'd love to be in a scenario like this one. But imagine that instead of having this kind of scenario, you have a scenario where actually both Z1 and Z2 affect X1 and X2 in exactly the same proportion. So Z1 is affecting X1 and it's also affecting X2, Z2 also this and this effect in here and this effect in here are the same. And let's say this effect in here and this effect in here are the same. That's why I'm using like the same colors. What that means in here is that you cannot separate the effects. So this case scenario, even though you have a just identified model based on the order condition, it's completely useless to you, okay? To separately identify two effects, you need two instruments that pull the endogenous variables in different directions. If they always pull in the same direction, you can't tell the effects apart, okay? So let's make a very clean summary regarding order versus rank condition. Okay, so the order condition, keep in mind, it checks whether you have enough instruments. Okay, and the rule and how to verify it, you simply need to count and compare number of instruments. How does it compare to number of endogenous variables? For the rank condition, the question that, or the thing that you're checking is, are the instruments independent enough? And the way you verify it is either a first stage F statistic or a matrix rank. Okay? But both must hold. Okay? Both must hold for 2SLS to work. Order is necessary, rank is necessary, neither alone is sufficient. For checking the rank condition, as I said, you need to check the first stage F statistic is above than 10. Some papers also report what is called the Craig-Donald statistic or the Clay-Bergen PAP statistic. These are more formal tests of the rank condition in multiple endogenous variable cases. You've got softwares like Stata that report these automatically when you use the IV9d command, but keep in mind, depending on what kind of work you're doing, and especially what kind of material you have been exposed to in class, if we're talking about an exam, then the tests that you need to mention are exactly the ones that you have been exposed to then. Now, why does this matter in practice? Again, a failure in the rank condition, even if it's a partial one, will lead to the same problems that we talked about weak instruments. So you're going to have imprecise estimates. You're going to have potential bias towards OLS, and most of all, unreliable inferences. Okay, so the rank condition is not a technicality. It's a substantive requirement about whether your instruments are doing enough independent work to identify all the causal effects. In applied work, rank condition failures often signal that you need to rethink your instrument set, basically. Not just add more instruments, but find instruments that genuinely pull the endogenous variables in different directions. Okay? So now you have everything you need. You have the general setup, you have the order condition, you have the rank condition. In the next video, we step back and bring the entire IV arc together into one clean reference summary before we move into the estimation. So stay tuned, and I'll see you in the next video.